Imagine standing at the edge of infinity, not metaphorically, literally, a boundary where the laws of physics don't just bend, they break. In 2019, the Event Horizon Telescope captured an image that billions of people saw, but few truly understood. That luminous orange ring glowing against the void wasn't just a picture of a black hole, it was a photograph of doom, the edge of space itself. The point beyond which nothing, not matter, not light, not time, can escape. But here's what keeps physicists awake at night. We don't just observe these cosmic guillotines from a safe distance. Recent calculations suggest something far more disturbing. Our entire observable universe might exist inside one. What if the universe as we know it, every galaxy, every star, every atom, is already falling into a black hole so massive we cannot perceive its boundaries? What if the expansion of space, the flow of time, even the existence of matter itself are merely symptoms of our descent toward an event horizon we will never see? Today, we journey through evidence that challenges everything we believe about our place in the cosmos. We'll explore discoveries that suggest reality isn't what it seems. We'll confront the mathematics that describe our cosmic prison. And we'll ask the questions scientists whisper in the halls of theoretical physics departments worldwide. Are we trapped inside a black hole? Prepare yourselves. We begin. April 10, 2019, the world witnessed the impossible made visible. 8 radio telescopes spread across 4 continents, synchronized to create an Earth-sized virtual telescope, captured radiation from the heart of galaxy M87, some 55 million light-years away. What they photographed was the shadow of a supermassive black hole, 6.5 billion times more massive than our Sun. But focus on that word, shadow. We didn't photograph the black hole itself. We can't. Black holes emit no light. Instead, we photographed the photosphere, the last photons that ever escaped, circling the drain at 99.9% light speed before being swallowed forever. That glowing ring marks the event horizon's outer boundary. Cross that line and the universe you knew ceases to exist. Astrophysicist Katie Bauman, whose algorithms helped process that image, described it as photographing a grapefruit on the moon. Yet what haunts researchers isn't the technical achievement, it's what the math revealed about the interior. Inside that darkness resides a singularity, a point where matter compresses to infinite density, where space-time curvature becomes infinite, where our equations quite literally produce the answer, undefined. In 1916, Karl Schwarzschild, serving in the German army during World War I, calculating artillery trajectories by day, solved Einstein's field equations by night. His solution described something Einstein himself found troubling, a region of space-time so warped that nothing could escape. Einstein wrote that the Schwarzschild radius does not exist in physical reality. He was wrong. Schwarzschild's radius defines the event horizon's location. For an object with Earth's mass, that radius is 9 millimeters. Compress our planet to marble size and it becomes a black hole. For our Sun, the Schwarzschild radius is 3 kilometers. For the monster at M87's heart, it's larger than our entire solar system. But here's the disturbing detail. The Schwarzschild radius scales linearly with mass. Double the mass, double the radius. This means black holes can grow arbitrarily large. How large? In 1935, physicist Arthur Stanley Eddington calculated that a black hole containing the mass of the observable universe would have an event horizon approximately 13.7 billion light-years in radius. The observable universe is 13.7 billion light-years in radius. Think about that. The paradox of perspectives. When astronaut Sarah falls toward a black hole, 2 observers experience 2 radically different realities. To her colleague watching from orbit, Sarah approaches the event horizon but never crosses it. Time dilation, predicted by Einstein's relativity, slows her clock relative to the outside observer. As she nears the boundary, hours become days, days become centuries. Her image freezes, redshifting toward invisibility, as even the light from her suit dims toward infrared, then radio waves, then nothing. Frozen in time, preserved forever on the edge of the abyss. She never crosses, not from the outside perspective, never. But Sarah experiences something entirely different. From her reference frame, nothing special happens at the event horizon. No barrier, no warning. She crosses smoothly, continuing her journey. She looks back and sees the universe blue-shifted, accelerating, entire epochs passing in seconds. The stars age and die, galaxies collide, billions of years compress into her final moments. She can still see out. Light from the universe still reaches her, but she can never return. She is causally disconnected from reality. Here's the question that haunts theoretical physics. Which perspective is real? General relativity insists both are equally valid. The mathematics describe two incompatible realities, both true, both observed, both experienced. This isn't philosophy, it's geometry. The curvature in space-time itself creates these paradoxes. But the evidence forces us to confront an uncomfortable possibility. What if we're Sarah? What if we're already inside, falling, experiencing the illusion of a stable universe, while the outside observer, if such a thing exists, sees us frozen on the threshold of something incomprehensibly vast? What if the expansion of space is just the geometry of our descent? In 1929, Edwin Hubble discovered something extraordinary while studying distant galaxies at Mount Wilson Observatory. Galaxies aren't static, they're moving, racing away from us in every direction. The farther away a galaxy, the faster it recedes. Space itself expands. This discovery birthed the Big Bang theory. The universe began as a singularity and has been expanding ever since. But consider the mathematics of falling into a black hole. From the interior perspective, space doesn't contract, it expands. The spatial geometry inside an event horizon undergoes exponential expansion in certain coordinate systems. Physicist Lee Smolin at the Perimeter Institute calculated that an observer inside a black hole would measure space expanding at an accelerating rate. They would see distant objects redshifting, receding toward an unreachable cosmic horizon. They would observe exactly what we observe. The expansion of space isn't evidence against living in a black hole, it's evidence for it. Light travels at 299,792,458 meters per second. Nothing moves faster. This creates a fundamental limit. We can only see regions of space from which light has had time to reach us since the Big Bang. We call this the observable universe, a sphere approximately 93 billion light-years in diameter, centered on us. Beyond that cosmic horizon, space exists, but we can never observe it. Information from beyond that boundary cannot reach us, ever. This horizon behaves mathematically identically to a black hole's event horizon in reverse. Inside a black hole, information cannot escape outward. In our universe, information cannot enter from beyond the cosmic horizon. The equations are mirror images. Cosmologist Nikodym Poplavsky at the University of New Haven demonstrated that torsion in Einstein-Cartan theory, a modification of general relativity that includes quantum spin, naturally produces these horizons. In his model, every black hole interior contains a universe, and every universe exists inside a black hole. We're not looking at distant space when we observe the cosmic horizon. We're looking at the event horizon's interior surface. In 1974, Stephen Hawking discovered that black holes aren't perfectly black. Quantum effects at the event horizon produce radiation, pairs of virtual particles where one escapes while its partner falls inward. This Hawking radiation has a temperature inversely proportional to the black hole's mass. For stellar mass black holes, this temperature is billionths of a Kelvin, effectively absolute zero. But for a black hole with the mass of the observable universe, The calculation yields 2.7 Kelvin. We detect radiation at exactly this temperature throughout the cosmos. We call it the cosmic microwave background, supposedly remnant heat from the Big Bang. But the temperature matches precisely what Hawking radiation from a universe-sized black hole should produce. The CMB appears perfectly uniform across the sky, same temperature in every direction. This troubled early cosmologists because regions separated by billions of light years shouldn't have identical temperatures unless information traveled faster than light. They invented cosmic inflation to explain it. But inside a black hole, the event horizon's interior surface naturally produces uniform radiation at a specific temperature. The uniformity isn't mysterious, it's geometric. In 1998, two teams studying distant supernovae discovered something that shouldn't exist. The universe's expansion isn't slowing, it's accelerating. Some mysterious force, dubbed dark energy, pushes space apart with increasing intensity. Dark energy comprises 68% of the universe's total energy density. We don't know what it is. It doesn't interact with matter or light, it simply exists. A uniform negative pressure permeating all space. Theoretical physicist Raj Pathria demonstrated that the interior geometry of a rotating black hole naturally produces negative pressure in certain regions. As matter spirals toward the singularity, the Coriolis forces from the black hole's rotation create zones of negative energy density, exactly matching dark energy's properties. Every black hole rotates. Conservation of angular momentum guarantees it. If our universe exists inside a rotating black hole, we should observe accelerating expansion caused by the parent hole's angular momentum. The strength of this acceleration should increase with time as we fall deeper into the potential well. Observations confirm this prediction. Dark energy's influence has grown stronger throughout cosmic history. The acceleration increases. When Sarah crosses the event horizon, she carries information, her memories, the data in her equipment, the quantum states of every atom in her body. That information vanishes from the external universe forever. But quantum mechanics insists information cannot be destroyed, ever. It's a fundamental law, as inviolable as energy conservation. Stephen Hawking wrestled with this paradox for decades. When black holes evaporate through Hawking radiation, the radiation appears thermally random. It encodes no information about what fell in. Yet information cannot vanish. In 2004, Hawking conceded he was wrong. Information must be preserved somehow. But how? Leonard Susskind proposed the holographic principle. All information inside a black hole is encoded on its event horizon surface, like a hologram. The three-dimensional interior is a projection from two-dimensional information encoded on a two-dimensional boundary we cannot observe. We might be holograms, shadows cast by information we cannot access. We're falling faster. Quantum field theory predicts that empty space, vacuum, seethes with virtual particles popping in and out of existence. Calculate the energy density of this quantum vacuum, and you get a number approximately 10 to the 120 times larger than observed dark energy density. This is the worst prediction in the history of physics, off by 120 orders of magnitude. Something must be canceling most of the vacuum energy. But what? Inside a black hole, the extreme space-time curvature affects vacuum energy differently. Physicist Emil Mottola at Los Alamos National Laboratory calculated that event horizon boundary conditions suppress vacuum fluctuations, reducing their energy density by factors of 10 to the 100 or more. The cosmological constant problem doesn't arise in universes within black holes. The boundary conditions naturally regulate vacuum energy to observed values. Our universe's vacuum energy isn't mysteriously small. It's exactly what black hole physics predicts. Time flows in one direction. Causes precede effects. Entropy increases. We age. We remember the past, but not the future. But physics equations are time reversible. Nothing in the fundamental laws distinguishes past from future. So why does time flow? The answer involves entropy, disorder. The second law of thermodynamics states entropy always increases. Time's arrow points toward greater entropy. But this raises a question. Why was entropy so low at the Big Bang? Why did the universe begin in an extraordinarily ordered state? Inside a black hole, the singularity acts as a low entropy boundary condition. All matter flows toward it, following geodesics in spacetime. From the interior perspective, you're always moving toward lower entropy at the singularity while experiencing increasing entropy in your local environment. This creates a natural arrow of time without requiring special initial conditions. Time flows because you're falling. Roger Penrose suggested the low entropy Big Bang is itself evidence we're inside something larger. The ordered initial state makes sense if it's a boundary condition imposed by a parent universe's black hole. Time flows because we're descending. Quantum entanglement connects particles across arbitrary distances. Measure one and you instantly know the other's state, even light years away. Einstein called it spooky action at a distance. In 2013, physicists Juan Maldana and Leonard Susskind proposed ER equals EPR. Every pair of entangled particles is connected by a microscopic wormhole, an Einstein-Rosen bridge. Entanglement and wormholes are the same phenomenon. This implies space-time itself emerges from quantum entanglement. Space isn't fundamental, it's a network of quantum connections between particles. But wormholes are solutions to Einstein's equations involving black hole geometries. If all quantum entanglement involves black hole-type connections, and our universe is saturated with entanglement, then we exist in a foam of black hole-like structures at quantum scales. Perhaps we don't just live inside a black hole, perhaps reality at every scale involves black hole geometries, fractal horizons all the way down. The most remarkable discovery involves recent experiments at CERN and Brookhaven. When physicists collide heavy ions at near light speed, they create quark-gluon plasma, matter that existed microseconds after the Big Bang. This plasma behaves like a perfect fluid with minimal viscosity. The mathematics describing this plasma are identical to the equations governing event horizons. Perfect fluids only arise in systems with event horizons. The evidence extends beyond cosmology into the realm of quantum reality. Black hole physics isn't just cosmic, it's fundamental. Standard general relativity assumes spacetime has curvature but no torsion. It bends but doesn't twist. Einstein-Cartan theory includes torsion from quantum spin. When matter with spin enters regions of extreme density, torsion becomes significant. Nikodym-Poplawski's equations show that torsion prevents singularities from forming. Instead of collapsing to infinite density, matter reaches a maximum density, about 10 to the 96th kilograms per cubic meter, then rebounds. This creates a big bounce. From the exterior universe, matter collapses into a black hole, but from the interior, matter bounces, creating an expanding universe inside the event horizon. Every black hole in our universe potentially harbors a baby universe. Every star that collapses births new spacetime. Our universe might be inside a black hole that formed in a parent universe, which itself exists inside another black hole, and so on. It's black holes all the way up. Physicist Lee Smolin proposed cosmological natural selection. Universes reproduce through black holes. Each universe's physical constants determine how many black holes form. Universes with constants favoring black hole formation produce more offspring universes. Over cosmic time, the multiverse evolves toward configurations maximizing black hole production, just as biological evolution selects for reproductive success. Our universe seems fine-tuned for life, but perhaps it's actually fine-tuned for black holes. The same conditions that allow stars to form, heavy elements to forge, and chemistry to complexify also maximize stellar collapse. Life is a side effect of black hole reproduction. This framework makes testable predictions. We should live in a universe optimized for black hole formation. Change any physical constant significantly, and fewer black holes should form. Multiple studies confirm this prediction. Our universe sits at a local maximum for black hole production. The implications are staggering. We're not just inside a black hole, we're inside a black hole that evolved to produce us, in a multiverse where universes compete for existence through black hole reproduction. Not everyone accepts these ideas. Sean Carroll at Johns Hopkins argues the entropy problems remain unsolved. Brian Greene at Columbia calls it provocative but incomplete. Many physicists dismiss the hypothesis as unfalsifiable metaphysics, but others find the evidence compelling. Abe Ashtekar at Penn State calculates that quantum gravity effects could validate the basic framework. Carlo Rovelli's loop quantum gravity suggests space-time granularity at Planck scales might create natural black hole interiors. The Princeton-based Institute for Advanced Study hosted a workshop in 2022 specifically addressing this question: do we live inside a black hole? Participants included Nobel laureate Roger Penrose, who argued that conformal cyclic cosmology, his model of eternal universe cycles, naturally includes black hole births. Penrose stated, "The mathematics doesn't care about our intuitions. If the equations suggest we're inside, we must take it seriously." This forces us to reconsider fundamental assumptions about cosmology. The Big Bang might not be the beginning. It might be a transition, a bounce, a birth from previous structures we cannot observe. Time doesn't begin, it transforms. How do we test if we're inside a black hole? The James Webb Space Telescope, launched in 2021, now observes the universe's earliest moments with unprecedented clarity. If our universe bounced from a previous collapse, we should see signatures in the cosmic microwave background, subtle anomalies and temperature fluctuations that standard inflation cannot explain. The Planck satellite detected such anomalies. The CMB shows an unexpected cold spot, a vast region 1.8 billion light-years across with slightly lower temperature. Conventional cosmology struggles to explain it, but black hole interior dynamics naturally produce such features. The Laser Interferometer Space Antenna, LISA, scheduled for the 2030s, will detect gravitational waves from black hole mergers across cosmic history. If these waves show unexpected polarizations or propagation patterns, it could indicate we're inside a rotating black hole whose frame-dragging effects twist space-time. Recent breakthroughs suggest the answer may come sooner. In 2023, researchers at the Max Planck Institute developed quantum sensors capable of detecting space-time torsion at laboratory scales. If torsion exists, we can measure it within a decade. If we're inside, what lies ahead? In standard black hole models, all matter eventually reaches the singularity, the end of spacetime. But Einstein-Cartan theory predicts no true singularity. Instead, we encounter maximum density and bounce. From our perspective, this appears as the far future, the heat death of the universe. Stars exhaust their fuel, black holes evaporate, entropy maximizes. Then, nothing. Or so we think. But if we're inside a larger black hole, the heat death might be a transition. Maximum entropy in our universe corresponds to minimum entropy at the bounce. We reach peak disorder, then reality reorganizes into a new universe with new physical constants. Not death, rebirth. This means the expansion of space eventually reverses. Billions of years from now, the cosmic horizon begins shrinking. Distant galaxies stop receding and begin approaching. Space contracts, not toward a big crunch, toward a bounce that creates successor universes. We're not heading toward oblivion, we're heading toward transformation. If this is true, it changes everything about our place in the cosmos. We're not random accidents in an indifferent universe, we're products of cosmic evolution, outcomes of a process that spans beyond our universe into vast multiverses we cannot observe. Black holes aren't cosmic monsters, they're wombs. Creation happens at reality's darkest points. Consider what this means for the Fermi paradox. We haven't detected alien civilizations because each sufficiently advanced civilization might create artificial black holes, birth new universes, and transcend this reality.
They don't spread through space, they create new spaces. Intelligence doesn't colonize the galaxy, it transcends the cosmic horizon. This framework suggests consciousness might play a fundamental role. If universes evolve through black hole reproduction and black hole formation requires complex stellar evolution, then chemistry, life, and eventually consciousness become evolutionarily advantageous. Perhaps consciousness itself influences which universes persist in the multiverse. Perhaps observation, the quantum mechanical act of measurement, plays a role in universe reproduction. Perhaps we're not merely inside a black hole, perhaps we're part of its reproductive machinery. The most profound implications emerge when we consider technological civilizations. If we can create black holes, and colliders like the LHC produce microscopic ones, we might eventually create stable black holes large enough to harbor universes. We could become universe parents. If our universe exists inside a black hole in a parent universe, what contains that parent universe? The answer suggests infinite regression. Black holes within black holes, universes within universes, boundaries within boundaries, extending infinitely in both directions. No ultimate ground, no final reality, just nested horizons, forever. This seems absurd, but mathematics doesn't care about human intuition. Georg Cantor's work on infinite sets proved different infinities have different sizes. The set of natural numbers is infinite, yet smaller than the set of real numbers. Infinity contains infinities. Perhaps the multiverse works similarly, an infinite hierarchy of universes, each inside black holes from parent universes, each producing black holes that birth child universes. No beginning, no end, just infinite structure. The most disturbing evidence comes from recent quantum gravity research. Carlo Rovelli's loop quantum gravity suggests spacetime is quantized, made of discrete units at Planck scales. If spacetime is quantized, then the number of possible universe configurations, while incomprehensibly vast, is finite. This means universe space, the space of all possible universes, must eventually repeat. Given infinite time and infinite hierarchy, identical universes must recur. You're not just inside a black hole, you've been inside this black hole infinite times before, and you'll be inside it infinite times again.
The simulation hypothesis argues we might live in a computer simulation created by advanced beings. If true, those beings live in a universe that might also be simulated, and so on. But black holes create the same hierarchical structure naturally, without requiring technology or programmers. Each black hole births a universe with new physical constants, effectively a new simulation with different rules. Perhaps simulations and black hole universes are the same thing. Perhaps advanced civilizations don't create simulations, they create black holes. The technology is identical. This resolves the simulation hypothesis's biggest problem. What simulates the top-level reality? There is no top level, just infinite recursion through black hole physics. We're not in a simulation, we're in something stranger. A self-simulating multiverse where black holes are the substrate and physical laws are the code. Recent experiments in quantum computing reveal something extraordinary. Certain quantum algorithms create computational spaces that behave like black hole interiors. The mathematical structures are identical. When you run quantum computations, you're not just processing information, you're creating miniature black hole-like geometries in Hilbert space. Computation and cosmology might be the same phenomenon at different scales. If we're inside a black hole and observation plays a role in quantum mechanics, then consciousness might affect the parent universe. The holographic principle suggests all information in our universe encodes on a two-dimensional boundary, the event horizon. When we make observations, we collapse quantum states, determining which potentials become actual. From the parent universe's perspective, information on the event horizon boundary evolves according to black hole thermodynamics. But that information includes our observations, our measurements, our conscious experiences. We're not passive observers inside a black hole, we're active participants in the boundary's quantum evolution. our choices, our observations, our consciousness might influence the parent universe's physics. This isn't mysticism, it's geometry. The interior observer's actions affect the boundary states, which affect the exterior observer's measurements. You're not trapped inside a prison, you're part of a system. Your observations matter. Perhaps the universe's greatest irony is this. We fear black holes as destroyers, as endings, as death itself. We imagine event horizons as final boundaries separating existence from oblivion. But if this hypothesis is correct, black holes aren't endings, they're beginnings. The Big Bang wasn't creation from nothing, it was birth from something. We already live beyond the event horizon, we've always lived beyond it, and we always will. The cosmic horror we imagine, being trapped inside a black hole, isn't a future possibility, it's present reality. Yet here we are, thinking, observing, existing. Perhaps horror is just misunderstood beauty. We began with a simple question. Are we trapped inside a black hole? We've journeyed through evidence suggesting the answer might be yes. The expansion of space matches black hole interior dynamics, the cosmic horizon behaves like an event horizon, dark energy matches negative pressure from rotation, the arrow of time points toward the singularity, quantum entanglement creates black hole-like geometries, the cosmic microwave background temperature matches Hawking radiation predictions. The mathematics doesn't lie. But trapped implies imprisonment. Maybe that's the wrong word. We're not trapped any more than fish are trapped in the ocean. We're not imprisoned, we're situated. This is our reality, our home, our cosmic context. Current scientific consensus remains cautious. Most physicists consider this hypothesis speculative but increasingly plausible. The evidence accumulates, the theoretical framework solidifies, the predictions become testable. Within the next decade, experiments may definitively answer the question. Until then, we exist in uncertainty, a liminal space between knowing and wondering. But perhaps uncertainty itself teaches the deepest lesson. We stand on the boundary between the known and unknown, between certainty and mystery, between existence and transcendence. This liminal space, this cosmic threshold, defines the human condition. We are creatures made of star matter, evolved on a planet orbiting an ordinary star, in a galaxy among billions, possibly inside a black hole among infinite black holes. We observe, we measure, we calculate, we wonder. And somehow, against all odds, we understand. The universe is vast, the mysteries are endless, but the journey, the questioning, the discovering, the marveling at reality's strangeness, that journey makes us human. We live inside a black hole, perhaps, but we also live inside wonder. And that makes all the difference.